Alright, so guys, today what we want to be looking at is vectors. We want to look at vectors today and Saturday night, God's Sphere Life, right? So vectors. So essentially, we want to differentiate between vector and scalar quantities, understand what is a position vector, understand what are equal, parallel, and collinear vectors, as well as scalar multipliers. And the next thing I want us to look at is the magnitude of a vector. All right, so I'll let y'all take this down. All right, so vector and scalar quantities. So there are two different kinds that we have here. So distance is considered to be a scalar quantity, and displacement is considered to be a vector quantity. Now, a scalar quantity that looks at size alone. So for example, this distance that we spoke of, this is just size. How far did you travel? Okay, distance looks at how far you travel. Another example is speed. So speed is another form of scalar quantity. How fast are you going? 30 miles per hour. Now look at the difference between scalar and vector. So vector now is a quantity that measures both size and direction. So for instance, if you have displacement, I'm saying that the displacement may be say 10 meters. So let's just say from here to here was 10 meters and this full distance here was 50 meters. So let me put that on so you could see it. Let's just say here was 50 meters in terms of distance, and the displacement was just 10 meters. Now, the difference between displacement and distance is that displacement, since it's a vector quantity, it has to say direction as well. So not just the size. So distance here says the size, which is 50 meters. Now, displacement has to say this person got displaced from here to here 10 meters, and we could roughly say that was about southeast. Let's just say it was southeast. Okay, so distance checks how far in terms of just distance alone, whereas displacement checks not only the displacement being 10 meters but the direction as well. So when we're talking about vector quantities, we're talking about size and direction. So another example is velocity, which is 30 miles per hour due east. So think of it this way. If you're driving down the road and your car is going at 30 miles per hour, that's just scalar because you just know the size of the speed you're going at. But if I'm saying now, oh, your velocity now, which is your displacement divided by time, we're not going to get into the specifics of it because this isn't physics. But the displacement part of it divided by time gives us velocity. Now, velocity cares about the direction. So if we was to say, oh, we're going 30 miles per hour due east, now we're talking direction. So you can see what direction the body is going at. Whereas speed is just the size. Okay, say someone move 50 meters, that's just size. If I say person was displaced 50 meters due west, now you're talking speed. Now you're talking size and direction. Sorry. Does that make sense? All right, so I want y'all to take this down and we continue going. So the key takeaway here is that scalar quantities represents size alone, whereas vector quantities represent size and direction. Now in maths, when we're talking about scalar or vector, as it relates to vector, we often tend to look at the direction, and we use direction by using up, down, positive, negative. So we get into what that is soon enough. So take this down and then we'll continue. All right, so vectors. So the journey from O to B can be noted as OB. Okay, so if you look at this, going from O to B, we consider this to be OB, and therefore we put an arrow here indicating direction. So this shows us that we're moving from O to B. So O to B can be noted as OB. So likewise, the journey from B to O can be denoted as BO. So see how the direction shows like we're moving from B to O. So think of it like this. If these were two countries, so let's say that the B was for Barbados and O was for Oman, you're going from Barbados to Oman. That's like going from B to O. Now, if you're going the next direction, we can call it OB. So if you're going from Oman to Barbados, it's OB. All right. So We can always represent vectors using letters. So I can also call this a particular letter. I could just call this vector B, and we could also use it as OB, BO, or we could represent it as a column vector. So typically when you have it like this, OB, we usually have that as a column vector. Now if I was to call this particular line the move from O to B, I just call it B, which you will see later on. That is when we're using a letter to describe a particular vector. So take this down and we continue. All of this is the introduction to vectors, the key things you need to know and understand of vectors. Alright, so the direction of a vector, when we refer to it in mathematics, we're looking at it from the x and y planes. So that's when we do the x-axis, y-axis. Alright, so those are the basic scales that we use to refer to direction. So for instance, if you have a positive x value, that means the number moves to the right. Okay, so a positive x value means the number moves to the right. What do you think a negative x value would mean?
Move to the left.
Excellent. So a negative x value would mean that you move to the left. All right, so let's talk about a positive y value. So a positive y value means that the number moves upwards. What do you think a negative y value would mean? Excellent. So a negative y value would mean that whatever that number is, the number of moves would go down. All right, so take this down. Very, very important. Fundamentals of vectors. Alright, so position vector. So whenever we're talking about a position vector, we're talking about it relative to the origin. And where's the origin? The origin is right here. Also refer to the origin's coordinate as 0, 0. Okay, so the origin is typically referred to as 0, 0. So if I was to tell you, oh, that's a position vector, what that means is that vector started off from the origin. All right, so that's what we refer to as a position vector. It started from the origin. So if I'm moving from the origin, or O, to another point M, O to M would be considered a position vector because it's moving from O, which is the origin, to a point M. So that is a position vector. Now, we usually write position vectors in the form of a column vector. Now a column vector, as you can see, this is a column. Columns run up and down. They are vertical. We have the x coordinate and the y coordinate. So we're going to talk a bit more about this in a bit. I'm just giving y'all a basic understanding of the key terminologies used to express vectors. So take this down, very important. All right, so let's look at this here, direction of a vector. So we have here the point A is represented within the coordinates 6, 8, right? So if I was to write this coordinate as a position vector from the origin, I would have to go 6 steps across and then 8 steps up. So as a vector, O to A, remember we're going from O to A, look at my direction. I would have to go 1, 2, 3, 4, 5, 6. I'm going to call it positive 6 because I'm moving to the right. So because I'm moving to the right is why I know it's positive 6, because we go 1, 2, 3, 4, 5, 6. And then I have to go up. So we always move across the x-axis first and then the y-axis. So then now we did the x part. Now we're going up. 1, 2, 3, 4, 5, 6, 7, 8. Now bearing that in mind, I can write my vector as O to A being 6, 8. Why 6, 8? Remember 6 is positive because I went right 6 times from O, and then 8 represents a Y, which is up or down. And since it's positive, it means that it's up. So then I go up 1, 2, 3, 4, 5, 6, 7, 8. So 6 to the right since it's positive. From O, we're starting at O and we're going to A. So 1, 2, 3, 4, 5, 6. Now 8 up because it's positive. 1, 2, 3, 4, 5, 6, 7, 8. So as a vector, O to A is 6, 8. Does that make sense, guys? Yeah. Lovely. Let's try a next one. So this one here, we're going from O to B. So how do you think we can get from O to B? We go 6 to the right, okay, so 6 across from O, and then we go minus 8 down, and the reason why we're going minus 8 is because we're going down. Once we're going down, we say minus 8. So I did 1, 2, 3, 4, 5, 6, and then I'll go down now to get to B. So that means I'm negative 1, 2, 3, 4, 5, 6, 7, 8. So therefore, O to B is 6, negative 8. Does that make sense? All right, there's two more like this now. So I'm going from O to C. So I always move from left to right, up and down. So I go here now from O, 1, 2, 3, 4, 5, 6. So I went to the left. Because I went to the left, it's going to be what? Negative or positive? Lovely, yes, because it's to the left. So now I'm right below the C, so I go up now. 1, 2, 3, 4, 5, 6, 7, 8. So I'm going up 8. So because I'm going up 8, I know that it's positive because up means positive. So therefore, minus 6 across and 8 up. Okay, so minus 6 and 8 up. All right, so this is how we write it: negative 6, 8. So negative 6 meaning we're going to the left 6 times. Remember our direction. Okay, so the size is 6, but the direction is negative on the x plane, which means you're going left. And then 8 is the size, and the direction part of it is up. How do I know it's up? Because it's positive. Now this last one here now. So O to D. In order to get from O to D, I would have to go 6 to the left and then 8 down. So because I'm going left, 6 is gonna be negative, and because I'm going down, it's gonna be negative 8. All right, so therefore our vector from O to D is negative 6 and negative 8. So negative 6, negative 8. And notice how I wrote it as a column vector. This is how we write column vectors. What you see here is a coordinate, but when we go from O to D, we write it as a column vector. All right, so that's essentially how vectors work from a basic point of view. And the fact that it's coming from the origin, this means it's what kind of vector? Position vector. Excellent. All right, so remember earlier we said vectors can be represented using letters as well. So this, for instance, is an example. So we have B, we have A. So when we talk about equal vectors, we're talking about vectors that have the same size and direction. So for instance, A and B here, they are equal, and they are equal because they are the same size and they're going in the same direction. Here as well, this particular A and this particular B, they are equal because they are going the same direction and they are the same size. All right, so guys, take this down. All right, so geometric relationships between vectors. So we talk about size. So size, it can either be the same size, twice the size, and opposite in direction, and so forth. That's what we mean when we talk about size. Another geometric relation is parallel. Whether they are parallel to each other, that's a geometric relationship. So they could have equal distances at all points. And then the next thing is collinear. They share the same line. So when we're talking about sharing the same line, we're talking about a straight line, not just any line, but a straight line. So these that you can see here, these vectors are different sizes. So these two are the same, these two are the same size, so that's their geometric relationship to each other. However, this one and this one, you can see that this one is twice the size of this. So that's another form of representing the geometric relationship of size. And as you can see, they're parallel to each other. These here are parallel, so they are the same distance apart. No matter where you put it, same distance apart, and they could also be different directions, but as you can see, same distance apart throughout. Now, collinear, they share the same line. So for instance, they share the same line, or they share a similar point. So for instance, A to B is collinear to A to C. You know, they're sharing the point A. Or you could also think of it as A to B and then B to C. They are two different vectors sharing the point B. All right, so take these down and also take the diagrams down to help you. Trust me, this helps a lot. So another very important thing that allows us to basically measure whether something has a geometric relationship to another vector is a scalar multiplier. Now the scalar multiplier is very important. Okay? It's basically the number that when multiplied to a vector can either increase the size, decrease the size, or change its direction. Okay? When we talk about scalar multipliers. Now, two vectors are parallel when they are scalar multiples of each other or equal. All right, so we're going to understand what that means and what that translates to mathematically as we go along our journey. So I want you guys to take this down. You don't have to take down the diagram part of it. Collinear vectors are so-called parallel vectors. They're not parallel, but they kind of like give parallel characteristics, which you will see when we do our calculation. So in essence, it's gonna seem like off the bat like, oh, they're parallel. No, it seems like they're parallel based on calculations. That's why I have it in quotation mark, but actually they are collinear if they share the same point. So let's say, for instance, here in the example below, the vectors a, b, and ac are collinear because they have a as a common point on the same line and are parallel in nature, in the sense of it seems like they're going the same direction, but the issue is they don't have the distance apart. So because they share the same trajectory is why we say they're collinear. Okay, so it's like almost like, oh, we could have been parallel, but we are going along the same path, so we're no longer parallel to each other. But when we do our calculations, it's gonna be easier for you to think that it's parallel when it's not, right? Because it's actually collinear. So when we say parallel in nature, we just mean in the sense of calculations, not the literal meaning of parallel. But when we say calculations wise, they would be scalar multiples of each other, which makes it appear that they are parallel. But in reality, we are able to distinguish between parallel and collinear if we look at a vector to see if they share a common point. So as we get deeper into this, you'll start to see what we mean. Alright, so when it comes to the magnitude of a vector, it's talking about the size, okay? So if you have a vector, we could actually represent it almost like a right angle triangle, and because of that, we could use Pythagoras theorem. Alright, so for instance, if I'm moving right, then I'm going up, that forms some form of a triangle. So my vector is this red one going from O to B. However, in order to get from O to B, I needed to go right then up, and look what that formed, a right angle triangle. So then we can find the size of OB using Pythagoras theorem. Another fun fact is when the size of a vector is 1 unit, we call it a unit vector. So you see now, if we want to refer to the magnitude of a vector, we write it like this. So as you can see, we have the straight brackets. That tells us, we're looking for the magnitude of OB. So take this down, very important stuff. Soon we'll get into some calculations and so forth. Alright, so we're putting it into practice. Everything that we did so far, we're going to put it into practice. So we'll do this here together. Okay, we'll do this here together so you can see how it's done. It says write OA as a column vector. So how do you think we could go about writing that as a column vector? So what we're going to do is OA means we're going from O to A. So if we're going from O to A, what that means is we go in from here. 1, 2, 3. Notice I started from O. 4, 5, 6, 7, 8. I'm right under A now, so I have to go up now. 1, 2, 3, 4, 5, 6. So I went 8 to the right and then 6 up. So 8 to the right and 6 up. So what that means is 8 is the X motion, meaning the left to right motion. So that's 8. And then I went up 6. So up and down represents a Y. So I have here now 8, 6. So that's my answer for the first question. Does that make sense? Good. Now check this out now. Instead of going from O to A, now I'm going from A to O. A to O. So A, always remember we move left to right first. So A to O, so we go 1, 2, 3, 4, 5, 6, 7, 8. Now, moving left to right, I moved left. So I should write my 8 as what? Yeah, it represents x, but what 8 will I be using? Positive meaning for x means left or right? Negative 8. Lovely. And then, if I was to go from here down to the O, I'm going to go 1, 2, 3, 4, 5, 6. So down 6 means we are negative or positive 6? Negative 6. So this represents O to A, and notice what A to O represents. You see what A to O represents? The same thing but different signs. Alright, so I want y'all to take this first part down just to process it, and then I want you to try and figure out what BC would be. What would BC be? And then we'll talk about it. Alright, so let's try BC now. So from B to C we start off at B. So we go 1, 2, 3, 4, 5, 6, 7, 8. So 8 to the right. So that's positive 8. Now I have to go up 1, 2, 3, 4, 5, 6. So I went up 6. So I'll say positive 8, positive 6. Okay. Alright. Do you guys follow this? Everyone understood what I just did there? Alright, so relationships. So state two geometric relationships between OA and BC. Now guys, based off of this, what can you say about the two of them just from observation? What can you say about two of them just by looking at them? Which makes them what? Parallel. Remember, when we are talking about geometric relationships, we are talking about these right here: the size, parallel, and collinear. So based off of that, they're parallel, and you can also see that both of them are the same size. They are the same size. Now this is how we go about proving it. So I want to see if OA is equal to 8, 6. Okay, so OA is equal to 8, 6. Let's put it down this way. OA is equal to 8, 6. And BC is also equal to 8, 6. Alright, so as you can see here, they're literally like the same thing. So what we do to back check to see if they're scalar multiples of each other, we always go like this. Alright, so we have 8 here, we have 6 here on this side, 8 here, and 6 on this side. So we divide them. So 8 divided by 8 is 1. What's 6 divided by 6? 1. So once you see both of them give you the same number, alright, once you see both of them give you the same number, what you can say is that they are scalar multiples of each other. Alright, so you can say OA and BC are scalar multiples of each other. Alright, I want y'all to write this down because this is going to be the blueprint for the questions that y'all do. Alright, so essentially what I did is prove that they are scalar multiples of each other because we had both of them getting the same number when we did this. That's how I know. Now there's only one exception that in a case like this that we do not look at, that is when we have 0 divided by 0. Okay, that's the only time that we look at it in a case like that. Alright, but other than that, once you get the same number here, we know it's good. So O and B are scalar multiples of each other. Whenever you're proving geometric relationships, whenever you're proving this, you have to look for that first. This is what you need to look for first. Okay, make sure they are scalar multiples of each other. Now, the first relationship that I'm comparing is the size. So OA and BC they are the same size. So this OA is 8, 6 and BC is 8, 6. Now, if OA was 8, 6 and say MN, let's just say we had MN was 16, 12, what do you realize about them? OA is half the size of MN. In other words, MN is double OA. But in our case, OA and BC are the same. So because they are the same, we say that they are the same size. Now the second thing that we look at, because they are scalar multiples of each other, right, they can also be parallel, because if you look at it, OA and BC are scalar multiples of each other and do not share a common point. Thus, they are parallel. If they shared a common point, they would have been collinear, but they do not share a common point. So look at this. OA is different to BC. They are two different points. That's why they are parallel. Okay, so as it relates to size, when we compare that, we notice the size and so forth. Alright, so I want you all to take this down and then we'll calculate the magnitude of OA. Okay, so this is giving you a crash course on all the nuances related to vectors with numbers. That's what we are focusing on right now. So we're just putting everything that we discussed theoretically together into a question, and then after I'll have you guys see it again in another example, and you continue to do examples until solidifies. So let's look at the magnitude aspect of it. So the magnitude, when it comes to the magnitude, we are talking about using Pythagoras theorem. So with OA, we said that OA is equal to 8, 6. So in other words, 8 means that we're going right or left? Right. So we're going right 8 steps. And then the 6 means we're doing what? We're going up 6. Good. So then now my vector O to A, from O going to A, is this. And this forms a right angle triangle. So what we can do is our good friend Pythagoras theorem. So we know that this is C, which represents the hypotenuse. So I can now say C squared is equal to A squared plus B squared. So this here, I could say this is A, this here is B. Alright. So then now C squared is equal to A squared, which is 8 squared, plus 6 squared. So then after I'll have C squared is equal to 8 squared, which is 64, plus 6 squared, which is 36. Now 64 plus 36 is equal to 100. So then what I can do now is find the square root of 100. So the square root of 100 is 10. So therefore the length of here is equal to 10. Alright, so guys, take that down. Alright, so with this one here, the first thing we're looking at is OF. OF. So if you check out OF, going from O to F, we have to go 1, 2, 3, 4, 5, 6, 7, 8. So 8 to the right, 8 to the right, and then after that we go 1, 2, 3, 4, 5, 6 down. So for question 1 is gonna be 8, negative 6. So 8 to the right and then 6 down. So that's for OF. Now just from experience now, we should know that F to O, all we're going to do is swap the sign. So if it's 8, it's going to turn to negative 8. And if it's negative 6, it's going to turn to positive 6. Alright, so bearing that in mind, we now know that OF and FO would be this here. But let's just back check FO now. So FO, for FO we would go 1, 2, 3, 4, 5, 6, 7, 8 to the left. And then we go 1, 2, 3, 4, 5, 6 up. So 8 to the left means negative 8 and 6 up is positive. Now let's look at number 3. Alright, these are our easy ones. So we go from here 1, 2, 3, 4 to the right. Okay, so 4 to the right means it's positive, so we put a 4, and then we go down. So down means negative, so I already know that's negative. Then we go down 1, 2, 3. So 4, negative 3. Okay, so that's basically for GH. Now number 4, we need to compare these two. So what I always like to do is put the one that has the larger numbers in terms of just size. I don't care about the negative or positive. I just care about the magnitude. So OF, I like to put these ones first when it comes to dividing. So 8, negative 6. And then I have GH, which is 4, negative 3. Now I'm comparing these two. So then I'll say 8 divided by 4 and then negative 6 divided by negative 3. You could do it the other way around too. It still works either how. So 8 divided by 4 is 2. Negative 6 divided by negative 3 is 2. So two of my values here are the same. So because they are the same, I know that they are scalar multiples of each other. So OF and GH are scalar multiples of each other. Okay, so this here allows us to justify whether it's parallel or collinear. Okay, alright. So the first thing I can say about them from this part here is that when I look at this, this is twice the size. So OF is twice the size of GF. So the first thing is size. So that's my first geometric relationship. Size. OF is twice the size of GH. Now in terms of the second one, I can say they're parallel because They are scalar multiples of each other, and they do not share the same point. So OF is different to GH. So they do not share the same point. So they are also parallel since they are scalar multiples of each other and do not share a common point. Okay, so that's for 4. Now, the last one, 5. So 5, Pythagoras theorem, once you see it like this, remember these fancy brackets tells us that we're trying to find the magnitude. So in this case, it's like saying GH, so G goes 4, -3. So GH is 4, -3. So it does not matter if it's negative or positive. So 4 across to the right and 3 down. So this is 4, this is 3 down or -3. So our vector is going here from G to H. Alright, so when I do Pythagoras theorem, here is C. So I can say C squared is equal to A squared plus B squared. So I can say that this is C, here is A, here is B. So therefore, C squared is equal to 4 squared plus -3 squared. So then C squared is equal to 4 squared, which is 16, plus 9. So therefore, C squared is equal to 16 plus 9, which is 25. So now we can find the square root of 25. The square root of 25 is 5. So my magnitude is 5. The next one, let's see the next one that we have, 3. So this one here shows a collinear because they're sharing some points here, right? So collinear. So because they share the same point, they're going to be collinear. However, remember what I told you the last time. So because it's 0 divided by 0, you're going to get infinity, but we know that they are supposed to be the same thing, right? So in that particular instance, you can use that. So I want you guys to try this now. Let's see what y'all come up with. All right, y'all ready to go through it now? All right. So OY, fun enough, OY does not move left or right on the x-axis. So it stays at 0. So then it's 0 at the top, and then it goes up 1, 2, 3. Therefore, it's 0, 3. So that's the one for OY. You guys got that? Lovely. Good. Now 2, OZ. So that doesn't move on the x plane either, but then it goes up 1, 2, 3, 4, 5, 6, 7, 8, 9, and stops right there. So we know then that that there is our answer, 0, 9. So then 0, 9 represents OZ. Now the question asks, what would ZO be? So we know that they just basically swap signs. So then after, since 0 is a neutral number, it's going to stay as 0. It'll stay as 0. And what we'll have here at the bottom is -9. Then now for question 4, very interesting one now. So we have OY, state the geometric relationships with OY and OZ. Now, off the bat, I could tell this here below, let's take this out. This here is 3 times, this yellow one is 3 times the size of the red one. I could have 3 of these red ones to form this full one right here. So OY is 0, 3, OZ is 0, 9. Now, we usually say that we divide it like this, but this is the one case where the zeros would not work. So in fact, let me do the other way, how I like to do it. Alright, so remember I like to put the biggest number first, so OZ 0, 9. So the 9 we have here, and then the OY, which is 0, 3. Okay, so then now what I could do is I could try to work that part out now and try to divide. So when I do that now, I would end up with 0. End up with 0 divided by 0, which cannot work, and 9 divided by 3. Okay, so then I will get 3 here, but in this case 0 divided by 0 would be infinity. However, I could see that to get from here to here, it's like it's 3 multiplied by the numbers. So anything multiplied by 0 is 3. Anything multiplied by 0 is 0. So therefore, even if I said 0 multiplied by 3, I still would have gotten 0. And then 3 times 3 is 9. So I know that they are still scalar multiples of each other. Okay, so therefore I could say that this one OY is 3 times the size of OZ. So OY is literally, OZ is 3 times the size of OY. So that means it takes 3 of these to make OZ. So that's one characteristic. So one is that size of the other. Then the next characteristic is they're collinear. Now how do I know they're collinear? Well, essentially they are scalar multiples of each other. One is 3 times the size of the other, but they share a common point. So because they share that point O, Okay, so we have OZ and OY. Usually when they don't share that point, we say that they are parallel, but in this case, they both share the point O, so we know that they are collinear. So that's it for that one. And then for 5, that should be easy. So OY, it's 0, 3. So then after, what we'll do is we say c squared is equal to a squared plus b squared. So then we'll end up with 0 squared plus 3 squared. So essentially c squared is equal to 3 squared, which is 9. We still got to find the square root of that. So we back to the size being 9. Alright. So yes guys, this is basically like a summary of what we did, understanding how to trace the vectors with numbers and how to actually go about finding the relationships between them as well as the magnitudes. Alright. So I want you guys to take this down, and once you take this down, I'll make any corrections. You can leave, but remember to continue to practice. Maths is about practice, guys. I can't stress this enough. You have to practice to do well in this subject. All right.